So it's a pleasure to thank the organizers for the kind hospitality and for the opportunity to visit this beautiful place and to participate in this workshop. So Gertrude has already given us a very nice introduction to heavy fermion systems and the general physics of these systems. And uh, today what I would like to do is be a little bit more specific and discuss what I would say are unexpected magnetic states that have been discovered in the superconducting phase of these particular family of heavy fermion compounds called the cerium-115 compounds. And so the outline of this talk is given in this, illustrated in this phase diagram due to Pagliuso that connects cerium-cobalt-5 to cerium-rhodium-5 to cerium-iridium-5. And these are the so-called cerium-115 materials. So we'll begin by discussing cerium-cobalt-5, which is superconducting, and show that there is evidence for both field-induced spin density wave as well as a spin density wave that's induced by replacing a small amount of the cerium by neodymium in this case. And we'll show that there's evidence that both of these spin density waves may be due to the particular D-wave symmetry of the superconducting gap of cerium-cobalt-5. Well, cerium-rhodium-5 orders magnetically at atmospheric pressure, but applying pressure, you can suppress this magnetism and induce superconductivity. And in this case, we'll show that there can be competing cerium-derived magnetism and a spin density wave magnetism, where these two magnetic orders develop from have very different origins, yet they both exist in the superconducting state of cerium-rhodium-5. And then finally, we'll come to a compound that has both rhodium and iridium, and in this particular compound, there is magnetism coexisting with superconductivity. And what we can do is we can apply a magnetic field to this material and suppress its superconductivity, in which case we find evidence for two completely different types of quantum criticality, so-called Kondo breakdown and spin density wave criticality. Both of these criticalities are hidden by the dome of superconductivity in the absence of a magnetic field, but this discovery allows us to connect in some way all the cerium-115s that are shown in this phase diagram, their superconductivity to quantum criticality. So before I continue, I'd like to particularly acknowledge two very talented postdocs, Priscilla Rosa and Yangkang Luo, who have made all the measurements, the new measurements that I will discuss today. And if I happen to use the word we, what I really mean is Priscilla and or Yangkang. So cerium-cobalt-5, as I said, is a superconductor. And when we cool cerium-cobalt-5 below a superconducting transition temperature of about 2 degrees, a very clear spin resonance develops in the superconducting state. And that's shown in this plot of the dynamic susceptibility as a function of energy, where we see this well-defined peak in the dynamic susceptibility that's centered at an energy of about 0.6 millielectron volts. The ratio of this resonance energy to the superconducting gap is precisely the same that ratio that is found in other materials. I apologize you can't see this so well here, but these are resonance energy versus energy gap for both electron and hole doped cuprates as well as some iron pnictides. So polarized neutron scattering experiments show that the fluctuations in the spin resonance have Ising-like symmetry. They're polarized along the tetragonal C-axis of cerium-cobalt-5. And this Ising-like symmetry is a consequence of the 4F crystal field environment. More recent neutron diffraction or neutron scattering experiments have shown that this resonance, while clearly appearing at a well-defined energy, appears also at a very well-defined wave vector, Q, that's equal to 0.45 a half. And this particular wave vector closely follows the nodal gap symmetry that has been found in cerium cobalt-5 by both point contact spectroscopy as well as scanning tunneling spectroscopy. So this wave vector at which this resonance appears seems to be a consequence of the particular nodal gap symmetry, D-wave nodal gap symmetry of cerium cobalt-5. Now, if we apply a magnetic field, this resonance splits into two modes, a higher energy mode and a lower energy mode. And this, the magnitude of this splitting is given, again, precisely by the G factor of the cerium crystal field doublet ground state. So it's a long extrapolation, but if we take the bold assumption and continue this energy versus field plot to zero energy, this lower energy mode should go to zero energy in a field of about 11 Tesla or so. And as we'll see, this is very close to the upper critical field of cerium cobalt-5. So let me just say again what this means. So as this energy mode goes to zero energy, that means that the fluctuations in this low energy mode should become static. There should be long-range magnetic order in a field of about 11 Tesla. And from the spectral weight, magnetic spectral weight in this low energy mode, we would expect an ordered moment of about 0.16 Bohr magnetons, and as I said, in a field of roughly 11 Tesla. So indeed, magnetic order is found in a field in cerium cobalt-5 in a field of around 11 Tesla, and that magnetic order actually appears in a range of fields between roughly 9.8 and 11 point something, 6 Tesla. And it exists, this magnetic order exists in the so-called Q phase, which is only inside the superconducting state of cerium cobalt-5. So this upper boundary here is the upper critical field of cerium cobalt-5. So this field-induced magnetism exists only inside the superconducting state of cerium cobalt-5. And neutron diffraction shows that this magnetic phase is a spin density wave, and it has an ordering wave vector of 0.45, 0.45 a half, and the ordered moment is about 0.15 Bohr magnetons, and those moments are ordered along the z-axis. In this phase, the magnetic correlation length of the spin density wave order is much greater than the superconducting coherence length, which implies that the magnetism and superconductivity coexist, and furthermore leads to the possibility that the magnetism and superconductivity order parameters are coupled. And theoretically, this coupling of the magnetic and superconducting order parameters can lead to what's called a Cooper paradensity wave, that is the intertwinement, essentially, of spin density wave order plus D-wave superconductivity plus P-wave superconductivity. And this possibility of a Cooper paradensity wave in this Q phase is a very interesting topic in and of itself. And I won't say anything more about it, but I would just bring to your attention that Roman Moshevich will be giving a talk here, I think, on August the 10th, where this will be the subject of his talk, and you'll learn all about it. The point I simply want to make today is that in this Q phase, this magnetic order has the same ordering wave vector, essentially the same order moment, and the orientation of those order moments is along the z direction. And this is precisely the same conditions that we know exist in this field split low energy modes of the spin resonance. And so this suggests that this spin density wave order arises from the condensation of excitons in the spin resonance that was predicted by Mikhail and Minaev. So assuming that interpretation of the origin of the spin density wave is correct, then in fact the existence of a spin resonance in the superconducting state of cerium cobalt-5 is a necessary precondition for the existence of spin density wave order in the superconducting state of cerium cobalt-5. Now, besides the magnetic field, replacing a small amount of the cerium by neodymium also induces magnetic order, and so far neodymium is the only substitution so far that shows magnetic order developing in the superconducting state, and that's reflected in this temperature doping phase diagram, where we see, for example, at 5% neodymium, the superconducting transition temperature of pure cerium cobalt-5 is reduced a little bit, but there's a phase transition that develops inside a superconducting state that's been seen by specific heat. And neutron diffractions shows that this anomaly in specific heat below TC is in fact spin density wave order. Here are the data. And lo and behold, the ordering wave vector here in this neodymium-induced spin density wave is 0.45, 0.45, a half. The order of moment, again, is somewhere between 0.1 and 0.14 5 Bohr magnetons, and that order of moment is along the Z direction. So this neodymium-induced spin density wave has exactly the same character of this field-induced so-called Q phase in pure cerium cobalt-5, and suggests that both of this magnetic order, neodymium-induced order, as well as the field-induced order have the same origin, namely the condensation of excitons in the spin resonance. So this magnetic order in the superconducting state appears as a very small anomaly in AC heat capacity divided by temperature. This large anomaly is the superconducting transition temperature. Here's the small anomaly associated with the spin density wave order. And Priscilla has shown that this spin density wave order is very rapidly suppressed with applied pressure. And we'll come back to this point in just a couple of slides. Now we've seen that there is field-induced spin density wave in the Q phase of pure cerium cobalt-5, and that replacing 5% of the cerium with neodymium also induces a spin density wave, in this case a zero field. So the logical question is, what happens if we apply a magnetic field to the sample with 5% neodymium? And Michelle Kinzelman and co-workers have just recently explored this question, and their answer is summarized in this field temperature phase diagram, where the vertical axis is the neutron scattering intensity. So what they find is that this zero field neodymium-induced spin density wave order is suppressed by an applied magnetic field, and that spin density wave transition goes to zero temperature in a field of about 8 Tesla. And at that same field, the so-called Q phase reemerges. So because the symmetry of this neodymium-induced spin density wave is identical to the symmetry of this field-induced spin density wave, this quantum critical point, implied quantum critical point at 8 Tesla, must be a rather unusual type of quantum critical point, because one cannot have a quantum phase transition between two order phases of exactly the same symmetry. And so this implies that this quantum critical point must somehow involve superconducting degrees of freedom. So I've mentioned that this Q phase that's found in pure cerium cobalt-5 hosts a Cooper pair density wave. I think it will be very interesting for future experiments to see if this neodymium-induced zero field spin density wave state also hosts a Cooper pair density wave, in which case this quantum critical point here must be extremely unusual. So now let's come to cerium rhodium-5, which I said orders antiferromagnetically at atmospheric pressure. This antiferromagnetic order is derived from the 4f electrons of cerium. The order of moment is very large in contrast to the spin density wave order that we've been discussing. It's much, much larger. And this ordering appears at a very different Q vector. So if we apply pressure to cerium rhodium-5, this Niel order initially increases and then begins to decrease. And there are a range of pressures below this pressure we call P1, where antiferromagnetic order and superconductivity coexist. But once the superconducting transition temperature becomes equal to the Niel temperature, at any higher pressures, there's no evidence in any experiments for this magnetism. It suddenly disappears, and at pressures above P1, there is only superconductivity, at least in zero applied field. On the other hand, Tucson Park and Georg Knebel have shown that if you tune cerium rhodium 5 to pressures between what we call P1 and P2, where there is only superconductivity in zero field, but now you add a field to cerium rhodium 5, you see first a superconducting transition in heat capacity, followed by a rather large anomaly in this case in the specific heat. The signals now field-induced magnetic order. So here we just show data at a representative pressure of somewhere about here, but you see very similar behavior at other pressures between P1 and P2. Now what's interesting is that this field-induced magnetism that exists in the superconducting state of cerium rhodium 5 is qualitatively different from this Q phase in cerium cobalt 5, because we can see here that this field-induced magnetism, while it appears first in the superconducting state, it extends into the normal state above the upper critical field boundary. So this field-induced magnetism in cerium that appears initially in the superconducting state of cerium rhodium 5 under pressure is qualitatively different from the field-induced spin density wave in the Q phase of cerium cobalt 5. And further, as shown by these solid symbols, this field-induced magnetism extends smoothly from below P1 up to pressures close to P2. And we'll come back to this in just a minute. So let me just back up. So the maximum superconducting transition temperature under pressure in cerium rhodium 5 is a little over 2 degrees. It's very similar to the, very close to the superconducting transition temperature of cerium cobalt 5. We know that cerium cobalt 5 is a D-wave superconductor. There's a body of evidence that suggests that the pressure-induced superconductivity in cerium rhodium 5 is also D-wave. So a logical idea was, what happens if you add 5% neodymium to cerium rhodium 5? And this is a problem that Priscilla Rosa has been studying. And she's used AC heat capacity measurements to look at this. And what she finds, her data are summarized in this panel here. So this sharp peak in the AC heat capacity at low pressures is just the antiferromagnetism. And then there is a hint of superconductivity that develops in the magnetic state that becomes more pronounced as we increase pressure a little bit more. But once we increase pressure a little bit to a little bit higher, evidence for this magnetic transition disappears. Instead, this large anomaly here now is the superconducting anomaly, and here's a small anomaly that we find that we associate with antiferromagnetic order. And the results of these data in zero magnetic field are summarized in this temperature pressure phase diagram, where we see that the Néel boundary decreases. There is a line of strongly pressure-dependent phase transitions that develops below the superconducting transition temperature. And these features in specific heat move rapidly to lower temperatures with increasing pressure. And in fact, they move down in temperature with increasing pressure at exactly the same rate, at least within experimental error, that we found in neodymium-doped cerium cobalt 5. So that suggests that this magnetism probably has the same origin as the magnetism in neodymium-doped cerium cobalt 5. But what we see is that there is a discontinuity in evidence for magnetic transition from pressures below P1 to pressures above P1. And we know that this magnetism is derived from the cerium F electrons, and it would suggest that this magnetism has a very different character. So just comparing these phase diagrams for a sample with 5% neodymium substitution and pure cerium rhodium 5, we see that qualitatively they're very similar to each other. and that the most notable difference is the appearance of this phase boundary that so far we've only been able to detect inside the superconducting state of cerium, cerium rhodium 5. So again, the question is, what happens to this neodymium-induced magnetism in an applied magnetic field? And we show some of those data in these panels here. So this, here we've applied a pressure such that the magnetism due to cerium is absent. And we see only this small anomaly due to the presence of neodymium. And now these are at a fixed pressure, and we're increasing the applied magnetic field. What we see is that this weak anomaly begins to split at a field of around 5.5 kilogauss and 11 kilogauss. This anomaly clearly is split. And the field evolution of these anomalies is plotted in this field temperature phase diagram here, where this higher temperature field split anomaly is shown by these squares. And what I just want to point out is that the evolution of these open squares in this neodymium dope sample is very similar to the evolution of field-induced magnetism in pure cerium rhodium 5. And so we associate this anomaly that gives rise to this phase boundary as being due to magnetism that's derived from the cerium 4f electrons. Then this would leave this anomaly at zero field and a small field that gets rapidly suppressed as being due to magnetism associated with the presence of a small amount of neodymium. So there's only 5% neodymium in this material. These neodymium atoms are just randomly distributed on cerium sites, and so it's very unlikely that the neodymium alone is inducing some direct dipole, or for that matter even RKKY type of magnetic order. And because, at least so far as we know, this magnetism develops only in the superconducting state, it again would suggest that this neodymium-induced magnetic transition has the same origin as the neodymium-induced magnetism in cerium cobalt 5, namely the condensation of excitons in a spin resonance. So again, if that interpretation is correct, then in principle, well, not in principle, there should be a spin resonance develop in the superconducting state of even pure cerium rhodium 5 at pressures above where there is no long-range magnetic order. Of course, this will be a very difficult experiment, but it should be a test, an important test of our interpretation. Okay, so now let's just turn to pure cerium rhodium 5 again. You've seen this phase diagram. And what I've mentioned is that in an applied magnetic field, one can follow this line of Néel temperatures to very low temperatures, where there is a magnetic quantum critical point around this pressure P2. So de Haas-van Alphen measurements have been made as a function of pressure, and results of those experiments are summarized in this plot of de Haas-van Alphen frequencies as a function of pressure, as well as in this plot of the effective mass of quasi-particles as a function of pressure. And what we see are two things. The first is that the effective mass of these quasi-particles diverge on approaching this pressure P2. That's expected at any sort of quantum phase transition. What is not expected at a conventional spin density wave quantum critical point is this rather abrupt change in de Haas-van Alphen frequencies as we go from below this pressure P2 to above this pressure P2. And these changes are most pronounced in these dominant sheets of the Fermi surface that are labeled alpha sheets, where we see that the frequencies of these alpha sheets go from something around 4 to something much higher than 4, near 5. So this jump in de Haas-van Alphen frequencies implies that the Fermi surface, certainly of this particular orbit, has become much larger. And this change in Fermi surface dimensions is not expected at a conventional spin density wave quantum critical point, but in fact is anticipated at a so-called Kondo breakdown quantum critical point that involves a critical destruction of the Kondo effect. So just by simple inspection, the phase diagram that's constructed by replacing rhodium by iridium, shown here, is very similar to this temperature pressure phase diagram of pure cerium rhodium-105. And we know that from de Haas van Alphen measurements, that the Fermi surface of cerium iridium-105 is so-called large. That means it has the comparable de Haas van Alphen frequencies as in cerium rhodium-105 at these high pressures. So this would suggest then that there should be a change from a small Fermi surface, a small Fermi volume in cerium rhodium-105 to a large Fermi volume somewhere as a function of iridium substitution, and furthermore we know that there's a magnetic boundary in this phase diagram as well. So this suggests that perhaps somewhere as a function of iridium substitution for rhodium, presumably near this boundary here, one might expect to find evidence for a so-called Kondo breakdown quantum phase transition. But unfortunately, because of strong disorder scattering in this substitution series, it's not possible to make these kinds of de Haas van Alphen measurements. So we have to use a different approach. So what we've decided to do is we've picked a sample that has 42% iridium. So that places it in this phase diagram at about this position here. So at this position, we have magnetism and superconductivity, but we know from neutron diffraction that this magnetism, in fact, this area in this phase diagram is rather complex in general. So if we cool a sample down at this composition of 42% iridium, it first enters a large moment incommensurate antiferromagnetic state, which is the same incommensurate magnetism that's found in pure cerium rhodium-105. If we cool it down just a little bit further, roughly a degree or so, a small moment commensurate antiferromagnetism appears, and it coexists with this large moment incommensurate antiferromagnetism. And finally, if we cool it down below a degree or so, we have superconductivity. So very, very complicated. Nevertheless, these phase boundaries at this composition are reflected in specific heat, which is shown here. So what we see is that there is an inflection point in specific heat divided by temperature at the onset of this magnetism. The peak in specific heat divided by temperature corresponds essentially to the development of this phase boundary here. And finally, there is a very small anomaly that's associated with the appearance of superconductivity. Okay. So let's just begin with electrical resistivity measurements. So from electrical resistivity measurements, we've studied the response of this sample to applied pressure, this sample with 42% iridium, and the results are summarized in this temperature pressure phase diagram. So the point I want to make here is that these resistance measurements show that the antiferromagnetic transition, the highest antiferromagnetic transition, is rapidly suppressed with increasing pressure. And above a pressure of about a half a GPa or so, any evidence for this antiferromagnetic order disappears in this superconducting state, basically. We just can't find any evidence for it. So what we've done is to apply a field of 9 Tesla. This field of 9 Tesla completely suppresses this superconductivity, so we can follow this Niel boundary to lower temperatures. And in this case, we've used not just the electrical resistivity, but the derivative of electrical resistivity, which we show in this plot closely resembles the specific heat, at least at atmospheric pressure. So this is at atmospheric pressure, the temperature derivative of the resistivity, this curve here. And for comparison, I show the specific heat divided by temperature here. So we can clearly associate this change in slope in specific heat with a change in slope in heat capacity, maximum, obvious maximum. And of course, there would be superconductivity if we had no applied field. So this similarity between the temperature derivative of the resistivity and specific heat allows us to track the magnetism to lower temperatures. And what we can see just by simple inspection is that evidence for magnetism, at least from the peaks of features in this derivative, exists to pressures at least of order 1 GPa or so. So clearly well above where it disappears in zero field. And the results of these experiments are summarized in this again temperature pressure phase diagram that's constructed for an applied field of 9 Tesla. And what we see is that the magnetic transition drops very rapidly. There's a clear change in character of the signature for the resistivity, but there's also a clear change in the pressure dependence of these features, and that's reflected in this shoulder here. So we see that this magnetism, any evidence for the magnetism disappears at a pressure of just a little over 1 GPa or so, and that there is a clear change in at least the pressure derivative, if not the nature of the magnetism, at a lower pressure. So superimposed on this pressure dependence of the nail magnetic ordering temperatures is the superconducting transition temperature that's measured now in zero field, and what we see is the TC, the superconducting transition temperature becomes a maximum, approximately where this magnetism reaches a quantum critical point. So the resistivity really isn't so sensitive to details of the Fermi surface or electronic structure at the Fermi surface, but thermal power is. And in this case, we show a summary of the thermal power measurements as a function of temperature for various fixed pressures. And what we see is that at low pressures, the thermal power approaches the origin with a negative slope, but at higher pressures, the thermal power approaches the origin with a positive slope. And these initial slopes in specific heat versus temperature are summarized in this plot here at various different pressures. And what we see is that there is a qualitative change, not only in the sign, but magnitude of the thermal power divided by temperature at this pressure, where there is a well-defined change in pressure derivative, pressure dependence of, whoops, sorry, wrong buttons. Let's go back. One more. Wherever I was. Sorry. There's a huge anomaly in the thermal power divided by temperature at this pressure, followed by a maximum in the thermal power divided by temperature, where the magnetic transition goes to zero. So this huge change in thermal power, because the thermal power is so sensitive to details of electronic structure, implies that there is a qualitative change in electronic structure at this pressure here. So we can compare these experiments to theoretical predictions, and this is why I hoped that Catherine would have been here today, among other things. So we're comparing to a theory of Catherine Pepin, who has calculated the thermal power as a function of a tuning parameter, in her case G, where she can now plot the temperature dependence of this thermal power divided by temperature for different values of a tuning parameter. In our case, this tuning parameter is just pressure. So in the case of a so-called Kondo breakdown quantum critical point, she finds a pronounced asymmetry in the thermal power divided by temperature, depending on whether you're approaching a zero temperature quantum critical point at tuning parameters that are less than the critical value of the tuning parameter, or whether you're approaching t equals 0 with values of the tuning parameter that have exceeded the critical value of the tuning parameter. So this pronounced asymmetry in the thermal power divided by temperature is reflected quite clearly in our experimental results, where now we've identified this pressure of about 0.6 GPa as being the quantum critical pressure. And so by this simple comparison of our experiments to Catherine's theoretical predictions, we would suggest that that there is a Kondo breakdown quantum critical point in this material and that involves a qualitative reconstruction of the electronic structure. On the other hand, at a conventional spin density wave quantum critical point, there is no reconstruction of the Fermi surface. And in this case, as one approaches the quantum critical point with decreasing temperature, the thermal power is essentially symmetric across this t equals 0 phase boundary as a function of the tuning parameter. And again, this is what we find experimentally for pressures about 1.06 GPa, which is where the magnetic transition goes to 0. So just from this comparison of theoretical predictions to experiment, we would imply that there are two qualitatively different types of quantum critical points in this material as a function of pressure. There is first a Kondo breakdown quantum critical point that is followed at a slightly higher pressure by a spin density wave quantum critical point. And both of these quantum critical points are hidden by superconductivity in the absence of an applied field. So we can then place what we know about these 115s in a broader context of a so-called global t equals 0 phase diagram of criticality for heavy fermion materials. So this global theory, so-called global theory, is constructed considering two different tuning parameters. One is magnetic frustration, that's labeled G, and the other is the magnitude of the Kondo exchange, JK, which we know is, in our case, is a function of pressure. So by varying these two tuning parameters at 0 temperature, C and co-workers map out this global phase diagram that includes, again now at t equals 0, the separation of an antiferromagnetic state with a small Fermi surface from an antiferromagnetic state with a large Fermi surface from a paramagnetic state with a large Fermi surface. Okay. And this line that separates any boundary that can, from a small Fermi surface to a large Fermi surface, involves the breakdown, critical breakdown of the Kondo effect. So we saw in pure cerium rhodium indium 5 as a function of pressure and field that there is a magnetic quantum critical point that also is accompanied by a change from a small to a large Fermi surface. In this example that we just discussed, cerium rhodium with iridium, we saw evidence for a sequence of Kondo breakdown to spin density wave critical points, which would imply a sequence of antiferromagnetic small to antiferromagnetic large to paramagnetic large type of quantum critical points. I haven't discussed either pure cerium iridium indium 5 or pure cerium cobalt indium 5 in any detail, but I can just simply tell you that they have large paramagnetic Fermi surfaces, and both of these are close to, there's a large body of evidence suggesting that both of these are close to a spin density wave type of quantum critical point. So from this body of information, as well as the known evidence for magnetic frustration in cerium rhodium indium 5 and the known increase in conduction electron F electron hybridization in the sequence cerium rhodium indium 5 to iridium doped to cerium iridium indium 5 to cerium cobalt indium 5, it seems now that we can with some confidence place these materials on this so-called global quantum phase diagram with cerium rhodium indium 5 here, this iridium doped cerium rhodium indium 5 material here, cerium iridium indium 5 and cerium cobalt indium 5. In all of these cases, crossing these boundaries has associated with it the development of D-wave superconductivity. So let me just summarize then by saying that we found now evidence for unexpected magnetic states that develop inside the superconducting phase of these cerium 115 materials These unexpected states are, in my opinion, a direct consequence of the proximity of all these cerium-115s to quantum criticality, where the buildup of entropy at low temperatures can be relieved then by the formation of orders such as unconventional superconductivity and coexisting magnetism. So in cerium cobalt-5, we've seen that a magnetic field as well as neodymium substitution for cerium induces a spin density wave order inside its superconducting state. And it seems that both of these spin density waves are a consequence of the existence of a spin resonance, which is a result of D-wave superconductivity, and that these magnetic orders, these spin density waves, reflect simply the condensation of excitations in that spin resonance. In the case of cerium rhodium-5, we've seen that again, neodymium replacing cerium with neodymium induces a zero field magnetic order, probably having the same origin of the spin density wave order in cerium cobalt-5, and that this zero field spin density wave order competes with the cerium-derived field-induced magnetism in the superconducting state of cerium rhodium-5. And then from the study of the iridium substituted material and what else has already been known about the cerium 115s, I think we now are able to provide a broader perspective on the substitutional phase diagram and the relationship between superconductivity and quantum criticality that underlies this superconducting phase diagram. And I'm sure there will be many other unexpected states that are yet to be found in this highly interesting family of materials. And with that, I'll be glad to try to answer any questions you might have. So thank you very much.